Okay, guys, so one thing we looked into in the magnification investigation that you were kind of forced to write a reasoning section on, but I want to improve our reasoning on this. This question, does object height, HO, does that affect magnification? So if your object has a different height, if it were taller, for instance, would it have a larger or smaller magnification, or would it stay the same? Okay. And I think what we saw is that if the object were taller, the magnification somehow was unaffected, even if it were taller. Okay, so let's draw some shadow diagrams of magnification. So 2 lines each, coming from a light source that's a pinpoint. And we'll draw this for our short object. You might want to copy down first before and pause real quick before you actually draw what I'm drawing. So for a short object, we'll call that short. And we'll draw a shadow diagram for our tall object as well down here. Skim the head. Don't go through the head, skim the head, skim the feet. Okay, so let's measure the height of the object for the small guy. I'm not going to use the distance formula this time. So to measure the height of the object, take out your ruler, and I get 2 centimeters for my object, and the height of the image is 4 centimeters. Okay, that's HO, and this is HI. Okay, now for the tall guy, I'm getting 6 centimeters. And looks like 12 centimeters. So let's calculate magnification for each person. The short person first. HI is 4, HO is 2. When you divide those, you get a magnification of 2. I should write centimeters. Centimeters cancels out, and there is no unit for magnification. For the tall guy, it is 12 centimeters on top, that's HI. 6 centimeters on the bottom is HO. And centimeters cancels, divide 12 by 6, and you also get 2. So the evidence would indicate that if you put a taller person in the same spot, which is important, that you would get the same magnification. So let's write a CER. I already have it written out for you, and you can put it in your notes to refer to answer this question. So we're going to claim object height does not affect magnification. We got the same magnification. So our evidence, our calculations, both ended up with a magnification of about 2, even when the object is taller. It is important that the distance of each object is the same. Okay? So as far as reasoning goes, we could say that this formula, di over do, that you had the same di and do. That is good reasoning, just saying, well, di and do were the same, it didn't matter on the height, so that's why we got the same magnification, because we plugged the same number. We could have plugged the same numbers in that formula every time, and it would have been the same magnification. And you can write that down. But you could also use the heights formula too. Magnification is a ratio. So remember, reasoning always comes from your notebook, all right? We're going to use these formulas. So using the heights formula, magnification is a ratio. A taller height of the object also means a taller height of the image. And since both increase when the object is taller, their ratio, when you divide them, stays constant. So if the numerator gets bigger and the denominator gets bigger when a taller object is put in the same spot, it forces both the height of the shadow and the height, basically when the height of the person that's on the bottom is bigger, so is the height of the shadow. So, you know, if you divide 4 by 2, or a bigger person like 6 centimeters, if you divide 12 by 6 for them, either way you get 2. So when the bottom of the fraction is bigger, so is the top of the fraction. And you end up dividing them and getting the same number. So that's how height works, is you might think, oh, it's bigger numbers you're plugging in when the person's bigger in that formula. Well, it's bigger numbers on the top and a bigger number on the bottom. So when you divide it, you still end up with the same answer for the height formula.